Diels-Alder reaction is going to be the topic of this lesson, and it turns out a Diels-Alder reaction is just a type of cycloaddition reaction, and a cycloaddition is one of the three types of pericyclic reactions. Now, for many of you, you may not actually even study any of the rest of these pericyclic reactions, and you may only study just the Diels-Alder. But a lot of you are going to be in the hook for all of these, and so the next 4 lessons are going to be on these pericyclic reactions, this one on the Diels-Alder, and then the next 3 kind of dealing each with one of these 3 in a larger context. Now, this lesson's part of my organic chemistry playlist. I'm releasing these weekly, so if you want to be notified every time I post a lesson, subscribe to the channel and click the bell notification. All right, so before we dive headlong into Diels-Alder reactions, once again, it is just one of these pericyclic reactions, and it's specifically a type of cycloaddition. And if we take a look at each of these 3 really briefly, so a cycloaddition typically involves 2 reactants combining to form a single product, and in the process is going to form a ring. That's a cycloaddition. Now, technically, these 2 species actually could be connected and stuff, and so you'd end up with one reactant going to one product in such a case. But usually it's actually 2 separate reactants, and that's what I like to think of as cycloaddition, where you're adding 2 reactants together to make a single product. All right, electrocyclic reactions are either ring closures, like in this case, but they're reversible, so you can actually do ring openings as well. And that's all they are, but you can distinguish them from the cycloadditions in the fact that you just got a single reactant and a single product every time. And then finally, sigmatropic rearrangements are going to be a fundamental rearrangement in your backbone here. So if you notice, in this case, we've got a cyclic motion of electrons here, forming a new sigma bond right here, but breaking a sigma bond right there. So we formed this new one here, but we broke one here, and that's what they mean by sigmatropic. So we're just changing the location of a sigma bond, if you will. So if you notice in all of these on the mechanism here, and we'll get into that mechanism specifically with each section, but they all involve the cyclic movement of pi electrons. That's kind of the hallmark of these pericyclic reactions. And by doing so, every atom gains a new bond and loses a bond so that the octet rule is not violated by any of them. All right, so let's take a look specifically at the Diels-Alder. It turns out that this cycloaddition right here is a Diels-Alder reaction. So if we take a look at it in a little larger context here. All right, so in this case, we've got the cyclic movement of electrons. So in this case, all these pi electrons, and once again, every atom in this, what we're going to form a 6-membered ring, is going to both gain a bond and lose a bond so that we don't violate the octet rule, but we're going to form a new sigma bond right here, and a new sigma bond right here, and then this pi bond is just going to change location to be a pi bond right there. So, and there's our product. Now, this is the most basic Diels-Alder, and we'll find out we can have different substituents coming off of here, and the result is that we're going to end up with different substituents coming off this basic structure right here. Now, we call this a 4+2. Let me write that a little better and line it up. So, a 4+2. I can't spell addition right now. So 4+2 cycloaddition, we've got 4 pi electrons moving from one reactant and 2 pi electrons moving from the other. So that's your 4+2 cycloaddition. And in this case, we got names we assign to these. This is the diene, and this one is the lover of the diene. So we call it the dienophile. I don't make this up. That is the real name that we use. So we got a diene and a dienophile. And we like to think of this as the reaction between an electron-rich diene and an electron-poor dienophile in this 4+2 cycloaddition. It is a concerted mechanism, meaning all of this happens in a single step. So, and in this case, the way we like to think of this, again, with the electron-rich diene and the electron-poor dienophile, is we like to think of electrons being donated from the diene to the dienophile. And if we look at the molecular orbitals involved with these frontier molecular orbitals, and we like to think of it as involving the highest occupied molecular orbital of the diene, donating electrons up to the lowest unoccupied molecular orbital of the dienophile. And so we'll find out that this difference in energy between these two is what we're going to characterize as the activation energy, and anything that can make that difference smaller speeds these reactions up. Anything that makes it larger slows these reactions down, and we'll learn some specifics on that. All right, so you've got to have a conjugated diene, hence the relevance in this chapter. And if you look here with this conjugated diene that we're using here with 1,3-butadiene, so the single bond between the two pi bonds is free to rotate. And it turns out we got two extremes for the two different conformations here, and obviously anything around 360, but these are the two extremes. Well, it turns out it's got to be in this conformation on the right when the reaction actually takes place. And so we give a name to this. So it turns out that we can't really call this cis or trans, although this looks like cis and this looks like trans, but cis or trans is formally around a double bond that can't rotate. This is actually around a single bond which can rotate. And so they give it a special designation. They call it S-cis, and this one S-trans. And the key is we say that the diene here has to be in the S-cis conformation when the reaction occurs. And so something else that can affect the rate at which a Diels-Alder happens is anything that favors formation of the S-cis formation speeds a Diels-Alder reaction up, and anything that hinders the diene adopting that S-cis formation, conformation is going to slow the reaction down. Let's take a look at some examples. All right, so the question on your study guide says rank these 5 in decreasing order of reactivity in a Diels-Alder reaction. So these are the dienes, these are the conjugated dienes, and if we're ranking them in decreasing order, then 1's going to be the fastest, and out of these 5, then 5 would be the slowest. And the way this works, this is all about adopting that S-cis conformation. Again, anything that favors adoption of the S-cis conformation speeds up a Diels-Alder reaction. Anything that hinders formation of the S-cis conformation is going to slow it down. Now, the single greatest thing that can either favor or hinder this is if the diene is part of a ring. And so like in this case, like if we take a look here, so this diene is indeed part of a ring. And if it's part of a ring, well, then the single bond between the two alkenes is not free to rotate like it normally would if it was part of an open chain. And if it's not free to rotate, then it's going to be in largely the conformation that it's in. In this case, this one's in the S-cis conformation, and it's always going to be in the S-cis. It's locked in the S-cis. And this thing, it turns out, is especially reactive in a Diels-Alder reaction. And so it turns out he would be the most reactive out of all 5 of these. Now, if we look at this one in comparison, on the other hand, so the single bond in between the two conjugated pi bonds here is also part of a ring, so it's not free to rotate. And in this case, though, it's locked in the S-trans conformation instead. And so it turns out this one is actually can't even adopt the S-cis conformation. It is completely unreactive in a Diels-Alder reaction, and so it's going to be ranked number 5. Now, after, having the diene being locked into a ring, which either speeds up or slows down the reaction, after that, it's really going to be about some sort of steric hindrance. When you've got these open chain ones, if there's steric hindrance when it adopts the S-cis, that's going to slow it down. And so we can see here, in this case, if we draw in some relevant hydrogens, so there's a hydrogen right there, there's a hydrogen right there, and one right there, and here the hydrogens are actually out here. And I guess if I'm going to do that, I should draw this one in as well. So we see that to adopt the S-cis conformation, you're going to have 2 atoms in the plane pointing in towards each other. And the bigger those are, the harder it's going to be to adopt this S-cis conformation. So the smallest they could be is if they're both just little tiny hydrogens. The worst out of these 3 anyways that could be is if they're both the methyl groups. And then the middle would just be a methyl with a hydrogen. And so the least steric hindrance when adopting the S-cis conformation is this middle one. So that'll be ranked 2nd. So, and then the most steric hindrance would be this guy with the 2 methyls. So he's going to be ranked 4th. And then this guy with 1 methyl, 1 hydrogen is 3rd. And so again, the single greatest effect was whether or not our diene was part of a ring. After that, though, it's just steric hindrance. So easiest to adopt the S-cis out of these top 3, and hardest to adopt the S-cis out of these top 3 due to sterics. Cool, so that's the first kind of question you might get about characteristics of the diene. But there's some other characteristics you might get as well. Let's take a look at another question. All right, the next question deals with which of these 3 dienes is going to react the fastest. And this one actually has nothing to do with sterics, but it deals with more of electronic effects. And so in this case, it turns out, we like to think of the diene as being electron-rich, and it's going to donate electrons from its highest occupied molecular orbital to the LUMO of the dienophile. And this difference in energy between the HOMO of the diene and the LUMO of the dienophile, that's essentially analogous to the activation energy of this reaction. And so If we want to speed this reaction up, we've got two options. I want to lower the difference in energy between the HOMO and LUMO here, so either I can raise the energy of the HOMO on the diene, or I can lower the energy of the LUMO on the dienophile, or both. And the way you accomplish this relative to the diene, well, it turns out if you want to raise the energy of the electrons, well, then you want to attach an electron donating group to the conjugated system. And we learned those electron donating groups back in the alcohol chapter when we dealt with like the acidity of phenols. And so it turns out your electron donating groups were either nitrogen or oxygen with a lone pair, like this guy. They were your strong donating groups, or it was just like a methyl group, like an alkyl group or something along those lines. So in this case, we got a strong donating group, we've got a weak donating group, and then this guy has nothing. And donating groups speed the reaction up. Now, it turns out if donating groups would raise his energy, speeding the reaction up, then withdrawing groups attached to him would have slowed it down. We don't normally do a Diels-Alder with withdrawing groups on the diene. However, on the dienophile, you want to lower the energy of the LUMO on the dienophile. Well, if electron donating groups raise the energy of molecular orbitals, it's actually electron withdrawing groups that would lower the energy. And so, whereas with the diene, you want to attach electron donating groups to speed the reaction up, on the dienophile, you'd actually want to attach electron withdrawing groups to speed the reaction up. And so the question we're dealing with at hand is dealing with the diene, and it just wants you to rank them in terms of decreasing order of reactivity again. I believe that's what it said. Yep, decreasing order of reactivity. And with the diene, again, the fastest is going to be the one with the strongest electron donating group, which is the oxygen with two lone pairs here. And it donates via resonance. And then this guy's a weak donating group and is second. And then this guy with no donating or withdrawing groups is third. And that's the second kind of ranking question you might see with regard to dienes. One involves like sterics, so in adopting that S-cis conformation, then one deals with the electronic effects here. So the next question on your handout is dealing with the dienophiles instead. And it says, wants us to rank these three in decreasing order of reactivity. And like we said just a second ago, the dienophile, you actually want to lower its energy to make the reaction go faster. And you do that by attaching electron withdrawing groups to your dienophile. So we've got an alkene, a simple alkene in each one of these cases. And your dienophile is typically an alkene or an alkyne. And in this case, we've got cyano groups attached to a couple of them and none over here. Well, it turns out that cyano group is an electron withdrawing group. And maybe that's easier to see if we draw one of them out. So you got this very, very polar carbon-nitrogen bond making carbon partially positive, which is why it's an electron withdrawing group. You could also actually look at it in terms of resonance, and we'll do this later, but you can push electrons to the more electronegative nitrogen and get a resonance structure that actually pulls the electrons away from these two carbons. So, and it's a minor resonance contributor, but it is a resonance contributor. So you can see that it's withdrawing electrons away from where we've got the alkene. So you could look at it either again from inductive effects or from resonance effects, and we'll do both along the way here. So, but the cyano group is definitely a strong electron withdrawing group. And again, that's when you got an electron withdrawing group on the dienophile, it lowers its energy, speeding up the reaction. And so in this case, having two of them is better than only having one, and having one is better than having none. And so order of reactivity is first, second, and third. So, and these are kind of the common questions you'll see in terms of ranking both dienes and dienophiles. So next we want to take a look at the stereoselectivity in Diels-Alder reactions. And first thing we'll do is take a look at when there are substituents on the dienophile. And if you look at this one here, so in this first case, your two withdrawing groups here, and I've just labeled them generically W, are cis to each other. And in the second case, we'll have them be trans to each other. So, and if we take a look at what the product ends up looking like, and again, with your most basic Diels-Alder reaction, you get cyclohexene here. Well, in our case now, we're going to have a W attached here and here, and if all I do is draw a straight line bond, that's not good enough. So because these carbons used to be sp2 hybridized in trigonal planar, but now they're sp3 hybridized, which means they're tetrahedral and they have a chance of being a chiral center. So as sp2 hybridized, there's no chance they're a chiral center, but now they have a chance of being a chiral center, and so it's not good enough just to draw straight line bonds. Convenient enough for us though, if they're cis on the reactant, they're going to be cis on the product here. And in this case, whether I made them both dashes or both wedges, it's the same thing. This is, it turns out, a meso compound, assuming these two withdrawing groups are identical. If they weren't identical though, then you'd get both enantiomers possible, both dashes or both wedges. So if we do this with the cyano groups here, and like we said, this is indeed a meso compound. Now, contrast that with having the two withdrawing groups on the dienophile being trans to each other. And if they're trans here, then they're going to be trans on the product. And in this case, though, even if they're identical, that's not a meso compound, and you'll get both enantiomers. So if we do this specifically with these cyano groups here, and there's your two products. So we've looked at the dienophile. Now we want to focus in on the diene here, and we want to look at the two end carbons on the diene, and they're going to have potentially have some groups besides hydrogen attached. They might just have hydrogens, but they might have groups beside hydrogens, and I've labeled them as O and I for out and in, and that's the contrast I want to make here. And notice I'm referring to this area right here where we're going to actually form the ring, and the two that point in towards that area I'm just labeling as in, and the two that point away from that area I'm labeling as out. And not everybody uses this kind of a convention. Some do, some don't. It's not like an official thing or anything. It's just my way of kind of categorizing this. And if you kind of take a look at what the product would look like, and so once again we're getting cyclohexene, and the key is that these two carbons right here are these two carbons on the product. And so they're sp2 hybridized on the reactant, they're trigonal planar, they can't be chiral centers, but now they're sp3 on the product, and they have the potential, depending on what's attached there, to be chiral centers, and that's why we're concerned with them here. So the way this works is that the two out groups will be cis to each other, and the two in groups will be cis to each other. And this can happen potentially in a couple of different ways. I mean, if these are the two out groups are identical and the two in groups are identical, that would be a meso compound, but that's not quite as common. So I'm actually going to take the time to draw this out. So, but the key is, again, that in a Diels-Alder reaction, the two out groups end up cis to each other and the two in groups end up cis to each other. So let's take a look at the following two examples here. And so first thing you want to do when you look at the two end carbons on the diene then is you want to label your substituents as out or in. So in this case, this one is out, but this one right here points in. And since one's out and one's in, they're going to be trans to each other on the product. So again, there's our most basic Diels-Alder product, cyclohexene. So with this carbon and this carbon, which amounts again to this one and this one, the in one, I'm just going to make that the wedge. So, and then the out one over here, I'll make the dash. So, and this is not a meso compound, so you will indeed form the enantiomer as well. Cool, and there's your product. And if we look at the similar example over here, in this example, now both methyl groups here both point out, and so they're going to be cis to each other on the product. I've started with making them both dashes, but I don't actually have to draw them. In fact, I don't want to draw them both being wedges because this is a meso compound. You can see that mirror plane right down the middle. So these are chiral centers, but it's a meso compound. And so whether I made them both wedges or both dashes, it's the same thing. So don't draw this one twice, just a single product in that example. Cool, and that's the stereoselectivity you should be concerned with on a Diels-Alder. You should realize if they're cis on the dienophile, they'll be cis in the product as well. If they're trans on the dienophile, they'll be trans in the product as well. And then on the diene, you got to worry about this whole out and in. And again, if the two groups both point out or both point in, they'll be cis in the product. And if one's out and one's in, then they'll be trans in the product. So that's kind of the way it works. So there we go. Go back. One in, one out, trans in the product. Both out or both in, cis in the product. All right, so now we're going to take a look at the regioselectivity of the Diels-Alder reaction. In this case, I'm going to deal with asymmetric diene and an asymmetric dienophile so that we can demonstrate this. And the question is, when these two lovely species add to each other and form a new ring, does it matter how they're oriented? So notice we could potentially flip this over, flip either one of these over. I'm going to flip the diene dienophile over, face this way. And it looks like then you just get a slightly different regioisomer. So if we look at it adding in this context, so there's our cyclohexene, we'd have the the donating group there, the withdrawing group here, whereas in this case, donating group there, withdrawing group there. Now, if we look at relationships here, so they often refer to this relationship right here as a 1-2 relationship between a donating group and a withdrawing group because they're on adjacent atoms, whereas here they would define this as a 1-3 relationship. So, and in this case, it turns out when you run this reaction with a donating group and a withdrawing group just like so, you actually don't observe the 1-3 product. So there's obviously some regioselectivity going on. So, but you only observe this 1-2 product. Now, one little quick thing about stereoselectivity for a second. Most of you aren't going to be on the hook for this, and you're probably not going to see examples where it's needed. So, but there is one little extra level of stereoselectivity. So if you've got groups both on your diene and your dienophile, well, now we can define in and out positions on the dienophile as well. And the ones that face towards the diene, where you're going to form the ring, those are the in positions. And the one that that point away are the ones that point out. Now, it turns out if you have the option, you should have your withdrawing group point out, away from the diene. Like it's, you know, the diene's electron rich and it's pulling electrons away from that electron rich diene. So kind of way to think about it. So if you could flip this over, but the reaction prefers to happen, it turns out, when the withdrawing group points away in one of these out positions. So, and I bring that up because all of these out positions are going to be cis to each other in the product, and all of these in positions are going to be cis to in the product as well. And so if we look back at this, I just drew straight lines because I didn't deal with this just yet. So, but in this case, this group, if we label it, points out, this one points out, and since they both point out, they're going to be cis to each other. So if we took this a step further, we could go, so, and make them both dashes. We could also make them both wedges, and here's where I'm going to get lazy. So oftentimes, the both wedges would just be the enantiomer, and if you want to show that you're making this compound and it's an enantiomer, you can just put plus minus in parentheses for some professors. I mean, it's kind of an accepted practice, but really it's up to your professor. But this is me being lazy instead of drawing it out with both wedges. So just an FYI. All right, so if we look at this next example here, so once again, we have a similar situation. If we kind of take a look at what the product might look like. So we've got a D attached right here and a W attached right here. And the question is there any reason we couldn't just flip one of those over? And once again, I'm going to flip the dienophile over, have it face like so. And if it reacts in this conformation, when the reactants are related to each other in that conformation, then you'd get this product. And once again, it turns out you're not going to get this one right 3. So in this example, you either had the option of getting the 1-4 or the 1-3, and it turns out the 1-3 is not observed. You only get the 1-4. So, and we're going to see it's for 2 different reasons, and we can explain it by resonance, but it's a nice convenient for us now because in either case, whether it's between the 1-2 and the 1-3, you don't get the 1-3. Between the 1-4 and the 1-3, you don't get the 1-3. And so we can make a rule, you just don't get the 1-3. So, and that's kind of the rule we can make with regioselectivity. And again, we'll explain this in terms of resonance here in a minute. So one other thing to note about this is I didn't draw any stereoselectivity here. And one thing is that this bond right here is in the plane. It's attached to an sp2 carbon, not an sp3. It's trigonal planar. That bond actually is straight. But this one, it turns out, you know, it doesn't have to have any relation to anything else. It's the only one that's on an sp3 carbon. And it could just be the wedge, or it could be the dash. I guess I should say it's the dash, or it could be the wedge. Either way, and maybe I could have just drawn this one and wrote plus minus as well and still been lazy. So, but that is the deal with regioselectivity in terms of predicting products when you've got an asymmetric diene and an asymmetric dienophile. Let's take a look at an example and let's explain it with resonance. All right, so we're going to take a look at 2 examples here. And in one example, we're going to have an electron donating group on one of the N carbons of our diene, and in the other one, we're going to have one of the 2 interior carbons of the diene to see the difference here. So if we look, first thing I want to do is actually redraw this in the proper relationship between the 2 reactants. So notice, like, here we have a withdrawing group, and let's label those. So here we've got a donating group. Here we've got a withdrawing group. Well, I want that withdrawing group to point away, so I'm going to flip this guy around. Also, right now, these two carbons end up right next to each other in a 1-2 relationship. If I flip this guy over, it'd be 1-3. Well, no, I want a 1-2. You can get 1-2, you're not going to get 1-3. So that's correct. So if we redraw this, and face that guy away, and now we can draw a product. So, and in this case, let's label these. This points out, so they're going to be cis to each other in the product. And so I'll make them dashes. There's an OCH3. There's the CN, and once again, that is the 1-2 product. And you could get this guy and his enantiomer. These could both be wedges as well. So the question is, well, why? Why do we get the 1-2 and why do we not observe the 1-3 at all? And once again, that comes down to resonance considerations. And if we look at this guy as an electron donating group attached to our conjugated system, he can donate electrons by resonance. And that would force these electrons over here and force these over here. And so we can take a look at a minor resonance contributor here. It has a positive formal charge on the oxygen, and then has a negative formal charge on the lower carbon here. And we can do the same thing with this guy. Let's draw out that cyano group. And we said we'd look at this, and now we're here looking at it. So we can withdraw electrons from the dienophile and pull these over here as well. And the minor contributor will get negative formal charge on the nitrogen. So it's going to leave a positive formal charge on this carbon right here. And so by orienting these relative to each other the way we did, the partially negative atom, according to resonance, is going to end up bonded to the partially positive atom. If I flipped this over, that wouldn't be the case. And that is actually what's governing this. And so this actually can attack with a lower activation energy when the partially negative and partially positive atoms end up right next to each other and end up bonded to each other. So that's kind of the deal. If we flip this over, that would not be the case. In similar fashion over here, so we can do something similar, and once again I'm going to redraw this. Face that cyano group the other direction. So, and in this case though, we have a problem, because now they're going to be in a 1-3 relationship, and we said, no, not going to get 1-3s in either case. So I need to flip this over. That was not going to work. I flipped it out, but it still wasn't lined up properly. So I do want to flip it out, but it needed to be, now these will be in a 1-4 relationship. And so there's our cyclohexene. We'll have the OCH3 group. Let's get that out of the way. Let's draw this prettier. So, and then the cyano group will be down here, and it could be a wedge or a dash. So you'll get a racemic mixture. And once again, this will be the 1-4 product, not the 1-3. And again, we don't observe the 1-3. So we got to ask ourselves the question. So again, well, what's going on in terms of resonance considerations here? Once again, we'll take a look at this electron donating group, and he can donate towards our conjugated system. And in this case now, still going to end up with a positive formal charge on oxygen. So, but in this case, negative formal charge on the top carbon. And same thing here, if we draw out that cyano group and do the same resonance we did on the last one, electron withdrawing group pulls electrons away. Leaves a negative formal charge on the nitrogen. And it's going to leave a positive formal charge on the top carbon. And once again, in orienting the way we did, the partially negative carbon ends up right next to the partially positive carbon, which again results in a lower activation energy. So, which is again why we only observe the 1-4 in this example and not the 1-3. So ultimately, that is what's behind the regioselectivity, and it's not uncommon for professors not only to require you to know this regioselectivity, but also to ask you to draw the resonance structures that explain the regioselectivity. So that's kind of why I've taken the time to show you those. All right, so now we need to take a look at Diels-Alder reactions with cyclic dienes, and these often confuse students the worst in terms of predicting any kind of the products from Diels-Alder. So once you make a cyclic diene, it means you're going to result in a bicyclic product. That just inherently confuses us. So if we take a look at what's going on here, so we're going to do the same kind of reaction here, and here's your most basic Diels-Alder if I cover that up, and your most basic Diels-Alder leads you to this product. Well, the question is, well, what do you do with this then in your most basic product? Well, again, it's attaching these two carbons right here, and I often find it convenient for students to kind of label the diene and dienophile, the 6 atoms that are going to form the ring. So label them on the reactant side and label them on the product side. And so in this case, I'm going to label this 1, 2, 3, 4, A, B. Those are the 6 atoms that are going to form a ring, and on the product here, that's going to be 1, 2, 3, 4, A, B. Cool. And now I can see the difference between the most basic Diels-Alder reactants and the ones that I have is this extra carbon right here that forms a ring. And it's an extra carbon that joins the ring between atoms 1 and 4, between atoms 1 and 4. And so in this case, we're going to have an extra carbon right there. These are chiral centers, so I'm going to show stereochemistry here. So there's an extra carbon there, and technically we wouldn't even necessarily draw that carbon in. We just connect the bonds, right? And so that's what this product might look like. Now this is bicyclic, and so for bicyclic compounds, we often represent them just a little bit different than this. And so we'll draw the same thing, we'll just draw it a little bit different here. So, and it turns out there's your 6-membered ring. And we'll label these in similar fashion. So we'll have 1, 2, 3, 4, A, B. We've got a double bond between 2 and 3. So, and then we've got between 1 and 4, we've got 1 extra carbon. And the way we draw that is like so. And we often erase just to the sides of this so we can see who's in front and who's behind. So, but this bond's just going in front of this bond here. And that's kind of the structure. And so you'll see this presented in both ways. And you've got to be familiar with both of them. You got to recognize it with both of them. And so, again, I find it convenient, especially with these cyclic dienes. You can technically do this with any of them, but labeling your reactants, your products, and label the 4 carbons of the diene and the 2 carbons of the dienophile. And if you don't want to use 1, 2, 3, 4, A and B, great. Come up with your own system. So, but it's often convenient to label them, again, on both the reactants and products, and then say, okay, well, what's different about what extra things do I have on my reactants that are not on the most basic Diels-Alder reactants, and then add them not only in the reactants, but then add it to the products as well. Now, one other thing we should concern ourselves with, so in our Diels-Alder reaction here, so there is just a little bit of stereochemistry we have to worry about, and technically, it's all encompassed in the rules for stereoselectivity we've learned, but it's going to show up in a little bit different context here. And so if we look at atoms A and B, when you have substituents coming off A and B, so what I've labeled A and B, and that's these guys right here. Well, it turns out we don't draw wedges and dashes when you represent a bicyclic structure like this. We just draw atoms in different positions. And so in this case, so we like to think of this, I like to think of this as like a hat. It's like a hat that just fits right on my head. And the ones that point down towards that hat, towards my head, are referred to as in the endo position. And the ones that point out away from that area are referred to as being in the exo position. Now, these 2 endo substituents, if they're there, are cis to each other, and these 2 exos are also cis to each other, but an endo would be trans to an exo. All right, so if you've got 2 groups like we do in this one right here, 2 cyano groups, those 2 cyano groups are cis to each other in the reactant, so they're gonna have to be cis in the product. And what we're gonna find out though is that substituents prefer the endo position, often called the Endo Rule. And that's something you gotta go with. And it turns out if you put the cyano groups, I lost a double bond there. Let's get him on there. But it turns out if you look at the transition state with the cyclic movement of electrons, so those electrons, those pi electrons overlap with pi electrons in the substituents. Like notice these cyano groups have pi electrons and stuff, only if they're in the endo position. And so by being in the endo position and getting that overlap with the pi electrons that are moving in the ring, or at least the ring that's forming, so that extra delocalization of the transition state lowers its energy, leading, and again, that leads to a lower activation energy. And so that's why there's a preference for substituents to be in the endo position. So if you have a choice, choose the endo position. So when your two substituents are cis, both go endo, preference over exo. Now again, if you had these trans, well then you'd have no choice but to make one endo and one exo. So there's no way around it in that case. All right, so that's the endo rule. So now we're going to work 3 examples and see how this plays out. And I'm going to represent these in the bicyclic fashion here because that's the most common way you'll see it. Like I said, you could see it either way, but you're probably going to more likely see it like this. So I'm going to draw it that way as well when we predict our products here. So, and once again, there's our 6-membered ring. We've got a double bond between atoms 2 and 3. So we got 1, 2, 3, 4, A and B. So, and then between, and I'll label it here, I guess, 1, 2, 3, 4, A and B. And again, my differences between my most basic Diels-Alder product and my most basic Diels-Alder reactants, I should say, and the ones that I have is this extra carbon between 1 and 4. So I need to make an extra carbon between 1 and 4. Cool, and then we've also got these 2 cyano groups on A and B. And so, and they're cis to each other, which means they're both going to preferentially get to pick the endo position rather than the exo position. And there is our product. Let's take a look at another one here. So here I've got a 6-membered ring instead of a 5-membered ring. So there's my most basic Diels-Alder product. And once again, we've got 1, 2, 3, 4, A and B. And 1, 2, 3, 4, A and B. And this is one of the more complicated ones, but by the time you label it like this, it makes it significantly easier. And so in this case, we've got 2 carbons to join between 1 and 4. And so instead of just making like a triangle up here, we actually need to go like so, and add 2 carbons. And then again, we'll erase right off to the side so we can see which bond's going in front and which one's behind. All right. And then on A and B are going to form another ring here. So now here's the deal. This is hard to draw. So, but we have an issue with those are cis to each other, and they both should have been in the endo position. So I got to figure out, well, how do I draw those in the endo position? Well, not like that. So got a couple of different options. Sometimes instead of drawing it like this, we'll revert to more of a drawing like this and come up with a way to do it. So, but we should be able to come up with this. We just got to make sure we draw the endo bonds first and make it work around that. So in this case, we'll draw this guy straight down, this guy straight down, then we'll connect them to an oxygen. Let's make that guy not so long. And then double bonds there. And now I've been able to make them both in the endo. And if that wasn't clear, if I wanted to make it even more clear, I could draw in the hydrogens to show my professor that I really knew what I was doing. The hydrogens are in the exo, but the 2 parts of that ring are definitely in the endo position. All right, so that's one way to do that. Now, in this one example, like I said, it's common on something like this for us to also represent it like this. And so I want to do that as well, just so you have seen it, because there's another special thing we do to represent this. And so in this case, we've got our most basic Diels-Alder product. And between 1 and 4, let's label this. 1, 2, 3, 4, A, B. Between 1 and 4, we've got 2 carbons. So, and in this case, I'm going to make these wedges to show the stereochemistry. Often show that. In fact, sometimes they'll even just darken the whole thing in so you see it's just a big wedge coming out. So, and then over here, we'll draw our ring like so. And there we go. But we got problems is that these are sp3 hybridized. They're newly sp3 hybridized, and I got to show the stereochemistry. Well, note if this points up and is a wedge, then these point the opposite direction and would be dashes. And so what we could do is this. except nobody does this. And I don't know why. I think it looks beautiful. But nobody does this. They don't like putting wedges and dashes in the middle of a ring most of the time. And so they do something else instead. So they'll keep those in the plane, but they'll make sure to draw the hydrogens in that are coming off these two carbons. And then they're going to show stereochemistry on those hydrogens. And so if these were supposed to be the dashes, well, then what does that make those hydrogens? Well, then those hydrogens would be the wedges. And by showing those hydrogens as wedges, it's implied that these two were the dashes. Cool. And like I said, you'll see both of these, and so I want to make sure you'll see and recognize both of those. All right, we've got one last example here, and this one is the only example we've done so far where the dienophile has been an alkyne instead of an alkene. But we'll follow the same process. 1, 2, 3, 4, A, B. We'll make our most basic Diels-Alder product and label it accordingly. 1, 2, 3, 4, A, B. And then we got to, well, what's different on my reactants compared to my most basic Diels-Alder reactants? Well, again, I've got a cyclic diene in this case, and so I've got to add one more carbon between 1 and 4. Cool, and then I've got a triple bond instead of a double. So one extra pi bond between A and B on the reactant means I have one extra pi bond between A and B on the product. And this is important because now when I go to add these cyano groups, there's no Endo Rule anymore because these carbons are not sp3 hybridized. They're sp2, so they're not tetrahedral, they're trigonal planar. And so there's no chiral centers or anything to show in this case, and you're just going to put these groups out at what it would look like if it was trigonal planar. So the biggest mistake students will make is they'll try and draw these specifically to make them look endo. Well, again, if these two carbons are sp2 hybridized, not sp3, there's no Endo Rule to apply. So I want to make sure you saw an example like that as well. All right, so we've got one last topic to talk about, and that's called the conservation of orbital symmetry. And you notice we got the pi molecular orbitals back up here, and I said we'd need some info about these for these pericyclic reactions. And if you recall, we labeled orbitals as like symmetric and anti-symmetric, and this is why, or this is part of the reason why anyways, the first application of why. And so we talked about, with the Diels-Alder, we've got an electron-rich diene and an electron-poor dienophile, and we're going to donate electrons here from the highest occupied molecular orbital of the diene into the unoccupied molecular orbital of the dienophile. And anything that raises the energy, i.e. electron donating groups, is going to lower the difference in energy between these, or anything that lowers the energy of the LUMO here of the dienophile, i.e. electron withdrawing groups, again is going to shorten the gap here and lower the activation energy. Now, it turns out for this reaction to even be possible, though, it turns out that the HOMO and LUMO have to be a match for each other. And what we mean by a match for each other is that's what actually is meant by conservation of orbital symmetry. So if we look, the symmetry refers to the whole symmetric and anti-symmetric. And so if we recall here, we've got symmetric, anti-symmetric, symmetric, anti-symmetric, and then over here, symmetric, and anti-symmetric. And so it turns out that the HOMO and LUMO that are involved in the reaction have to have the same symmetry, and they're both anti-symmetric. And so we'd say that there is indeed conservation of orbital symmetry, and this reaction will be allowed. So if we see what's going on here, so when you're diene and dienophile here, so if we take the diene and the dienophile here, and instead of looking at it again from our line angle formula, we're going to look at it as the approach of the molecular orbitals involved, the HOMO for the diene and the LUMO for the dienophile. And if we're going to take a look at how this looks, so again, so there's the highest occupied molecular orbital for the diene. And then the LUMO for the dienophile. And what you're going to find is that one is going to come right on top of the other. So here I've kind of drawn it to where like the dienophile is going to, the diene is going to come right on top of the dienophile. And what we're going to get is overlap occurring here between the orbitals. And they have to be in phase. And so in here, they're both in phase, and in here, they're both in phase. So, and it turns out when the bottom side of one molecular orbital is meeting up with the top side of the other molecular orbital on both sides, we call that a special name. We refer to it as suprafacial. And we'll allude to this later when we get to the lesson on cycloadditions in general. So, but it turns out when you're going from bottom to top, that's superfacial, and when you're doing it on the other side, well, that's also superfacial. And so this interaction overall we'd call superfacial. Whereas it turns out we'll have an option in other cycloadditions, not the Diels-Alder, where we have something called superfacial and anterofacial, where instead of one going from bottom to top, it's actually going to go top, top, bottom, bottom, like matching them up on one side only. And so in that case, it would be called suprafacial and anterofacial, but we'll allude to that later. But the Diels-Alder doesn't have to worry about that. So because the orbital symmetries match, they're both asymmetric. And so I know, if you notice what is true about them both being asymmetric, so is that the opposite ends of an asymmetric orbital, they don't match. For a symmetric orbital, they do match. For an asymmetric orbital, they don't match. For a symmetric orbital, they do match. So just the end lobes of the molecular orbital picture, if you will, is all I'm concerned about. Again, there's not really p orbital at the end here. It's one big, area of electron density and yada yada, but the end parts are the parts I'm concerned with. And in this case, the ends here are opposites and the ends here are opposites. And if that's the case, they'll be able to match up. And so they either both had to be asymmetric or both antisymmetric. And in the Diels-Alder, they're both antisymmetric, which is why, again, there's conservation of orbital symmetry. And that is actually what makes this reaction allowed. Now, if you've found this lovely lesson on Diels-Alder reactions helpful, would you give me a like and a share? That'll make sure the widest audience of students needing help with Diels-Alder reactions possible will see this lesson. If you're looking for the study guide that goes with this, if you're looking for Diels-Alder practice problems or final exam reviews or practice final exams, anything of that sort to help you in your organic chemistry course, check out my premium course on chadsprep.com.